This is the first part of the dawn of electromagnetism, which is a part of the four fundamental forces. Like the last video, this video will alternate between mathematics and history. So stay tuned for this amazing video about the mathematics and history of electromagnetism. What is light? Is light a wave or a particle? Well, to truly understand this, we must travel back in time to the time of the ancient Greeks. We have two main individuals. We have Pythagoras and Plato. Pythagoras was a very prominent mathematician who believed that everything was number. Plato, on the other hand, was a very prominent philosopher and wrote the book The Republic. Now, Pythagoras and Plato believed in two contrasting views of the source of light. Pythagoras believed that light came from an external source, whereas Plato believed that light came from an internal source. Now we know that one of these must be correct. We know that Pythagoras was much more accurate, since light does indeed come from an external source, which is the sun. We must go forward in time to meet Isaac Newton and Christian Huygens. Isaac Newton believed in the corpuscular theory of light, which practically just stated that light is made out of corpuscles, which in essence are just particles. Christian Huygens, on the other hand, believed in the wave theory of light. So is light a particle, or is light a wave? Well, today we know that light is both a particle and wave, established by the wave-particle duality in quantum mechanics. However, at the time, there was no such wave-particle duality. So did scientists believe Isaac Newton's corpuscular theory or Christian Huygens' wave theory? Well, scientists decided to believe in Isaac Newton's corpuscular theory at the time because Isaac Newton was such a well-known scientist. Note that Isaac Newton's corpuscular theory was indeed incorrect because it couldn't describe all the phenomena associated with light. But scientists did indeed decide to support Isaac Newton's corpuscular theory because he was a well-known and respectable scientist. This does not mean that Christian Huygens' theory was wrong, because as we will see later, Thomas Young showed that light can actually be a wave. The field of electromagnetism is reliant on the study of vectors and vector calculus. However, to truly understand the mathematical interpretation behind electromagnetism, we must properly define the notion of a vector. So what is a vector? Well, a vector is anything with a magnitude and a direction. Where a magnitude is just a size and a direction, well, that's pretty self-explanatory. It's just a way that something points. Well, let's define the notation of a vector, and then proceed forward. A vector is usually denoted by a lowercase letter, we'll call A, and has an arrow on top. So this is called vector A. So this is vector A, and we denote it like this. Well, how can we write vectors? Or how can we represent vectors? Well, there are two ways to represent vectors. Well, we can write them in the algebraic form, and we can write them in the graphical form. So what is the algebraic form? Well, the algebraic form is just writing it in terms of vector notation. So we can write the vector A is equivalent to the vector 1, 2. So this is the vector A. Now, how do we graph this vector? Well, we'll get to that in a little bit. But let's first define the operations on this vector through this notation. So let's first describe this notation. This notation is a vector that has 2 rows and 1 column. So we call it a vector with a dimension of 2 by 1. Now notice there are 2 components, which means that there needs to be 2 dimensions or 2 axes on the coordinate plane to describe this. Now, here's another important point. To add another vector to this vector, all we do is we add the components. So we have vector V, which is equivalent to 2, 1. V plus A is equivalent to 2, 1 plus 1, 2, which is just 3, 3. So this is how we add vectors in this notation. So as we've seen, we've just defined vector A, we've written it as a column vector, and we've added them together to get 3, 3. Subtraction works the same, except that if we have V minus A we would write 2, 1, minus 1, 2, which negates the components, which becomes 2 minus 1, which is just 1, and 1 minus 2, which is negative 1. So as you've seen, we've defined addition and subtraction. Well, what's the difference between a vector and a matrix? A matrix has more than one rows and more than one column. Now this is different from a vector. A vector can have multiple rows and one column, or it can have multiple columns and one row. But a matrix has definitely more than one rows and more than one columns. So that's the difference between a vector and a matrix. So this is basic vector addition, subtraction, and the notation of a vector. Notice we could write it as a row vector. A row vector is just a vector written like this. So we could write A as, well, we'll define a new vector now. We'll call it A prime, can be written as 1, 2. This is called a row vector, and it has a dimension of 1 by 2, where there's 1 row and 2 columns. Okay, so now that we've talked about vectors and their notation algebraically, we can now progress to the graphical side. So how does a vector look like on a coordinate plane? Well, that's pretty simple. A vector is just an arrow pointing in a direction. We'll call this vector v. And it has a magnitude, which is the size or length of this vector, and it points in a direction. So even if we have a vector of the same magnitude pointing in a different direction, this vector is different from this vector. So as you've seen, we've now just shown how a vector looks like. But there's one important question. How would we graph vector A onto this coordinate plane? So A, recall, is 1, 2. How would we graph it onto the vector plane or the coordinate plane? Well, to do this is pretty simple. The reason there are 2 components in this is due to the fact that there needs to be 2 axes or 2 dimensions. So in other words, this represents the x-axis in a sense, and this represents the y-axis in a sense. So therefore, in order to draw this vector, we would have to go 1 piece to the right. So this is 1, and 2 up, 2 in the y. So 1 on x, and 2 in y, so that's the point over here. And we draw an arrow from the origin, ending at this point. And this will be our vector. We draw it more neatly. This will be vector A. So this is vector A. We scale this up a little bit, so it'll be more easy to see. We'll find that this is 1, and this is 2. The vector point like this. So this is vector A. And that's how you graph vector A, and that's really simple. Well, before we go on to how to add 2 vectors, it's crucial to introduce unit vectors. A unit vector is a vector that has a magnitude equal to 1. So a unit vector is a vector in which the magnitude equals 1. Now there are 3 fundamental unit vectors, I hat, j hat, and k hat, where I hat points in the x direction, j hat points in the y direction, and k hat points in the z direction. Now, due to the fact that we're only dealing with 2-dimensional vectors over here, we do not need k hat. But let's draw I hat and j hat. I hat is 1 over here, so this is I hat, 1 on the x-axis, a unit vector with length 1 on the x-axis, and j hat is a unit vector with length 1 on the y-axis. This is j hat. So we have I hat and j hat, and these represent unit vectors on this coordinate plane. So we can describe any vector through just I hat and j hat. Well, how do we do that? Well, recall that 1 and 2 are just scalar quantities. If we remove the signs from here and just have 1 and 2, well, obviously they're just scalar quantities. They're just numbers. We have 1, 2, 3, 4, 5, 6, 7, etc. They're part of the integers. So you know that 1 and 2 are just scalar quantities. So rather, in order to introduce more vector notation for them, we can write vector A without the brackets like this. A is equivalent to I hat plus 2 j hat. The reason we don't have a coefficient in front of I hat is because 1 times I hat is just I hat. So we essentially take the first value on top, multiply it to j hat, and take the second I hat, and then take the second value and multiply it to j hat. So we have I hat plus 2j hat, and that's the representation of this vector. So as you can see, we've just gotten this vector. Now, let's define how to add two vectors graphically. How would we add two vectors? Well, keep this in mind because we will use this as an example. So let's say we have a vector like this. This is I hat, and we have another vector, which is 2j hat. So something like this. Notice that when you multiply a vector, a unit vector, by a scalar, or which is 2 in this case, we just multiply its magnitude by that scalar. In this case, the magnitude is 1, so 2 times 1 is 2, so the length of j hat would be 2, and well, the length of 2j hat would be 2 in this case. So let's say we want to add these two vectors. How would we do that? Well, we take the first vector, put it like this, and let's erase this for now. We take the second vector and put it on the tip of the first vector, which is 2j. Then we draw a line, or a vector, from the tail of this to the tip of that. Or we can draw it more neatly, like this. And this would be I hat, this 2j hat, which in this case is just the vector a. And that's how we would add two vectors using the tip to tail method. So we essentially take the first vector, put it there, take the second vector, put it on the tip of that, and draw a line from the tip to tail, or in other words, over here, and we call this the tip to tail method. Notice that the vector points in this direction. So that's how we add two vectors. Now how do you subtract two vectors? Well, subtracting two vectors is the same thing. Now, what's the intuition behind it? Well, let's say we have I hat over here, we have minus 2j hat. Well, obviously I hat minus 2j hat, let's write it in vector notation. Obviously this is just one coefficient and this is negative 2. If we draw it on a coordinate plane, how would it look like? Well, we would have 1 and going negative 2 down, so it would look like this. So this is how this vector would look like over here. Now let's add I hat and negative 2j hat together. Well, first let's draw I hat. This is I hat. And now, in order to draw minus 2j hat, all we just do is we just negate 2j hat. How do we negate a vector? Well, if a vector is pointing in this direction, negating it would make it point in this direction. If a vector is pointing in this direction, negating it would make it point in this direction. Therefore, if a vector is pointing in this direction, negating it would make it point in this direction. So we just reverse the direction when we're negating something. So we reverse 2j hat's direction, which means it points like this. This is a negative 2j hat, and we do the tip to tail method. And this would be I hat minus 2j hat, and as you can see, it coincides with the drawing here from the origin. So therefore, that's how you add, and that's how you subtract two vectors graphically. And now that we've talked about that, we can make this section to an end. Thomas Young was one of the most influential scientists who truly helped shape our understanding of light. But how did he do it? Well, he did it through the double-slit experiment. So let's generalize the double-slit experiment. So consider a beam of light, and then a sheet with two slits. Behind that sheet, you have another sheet without two slits. Now we'll call the sheet with two slits sheet A, and the sheet without two slits sheet B. Let's say you shine the beam of light through sheet A. What pattern would you get on sheet B? Well, if the light was composed of particles, you would just get light behind those two slits on sheet B. However, if the light was composed of waves, you would get an interference pattern. In other words, you would get light where you wouldn't expect it to be. So what did Thomas Young observe? He observed that there was an interference pattern, so there was light where you wouldn't expect it to be. And this therefore proved Christian Huygens' wave theory of light, because in order for there to be an interference pattern, light would have to be a wave. The dot product is one of the most significant tools in all of vector analysis. So what is a dot product? Well, the dot product is a way to multiply two vectors such that the result is a scalar quantity. Now in this section, we'll be solving these two problems using the formulas associated with the dot product. So let's begin without further ado. So what's the notation for the dot product? Well, let's say you have a vector A and a vector B. To take the dot product of them, we simply write a dot. And boom, there you have it. We have the dot product. Well, what's the official formula for the dot product? Well, the official formula, in the sense, is the magnitude of A times the magnitude of B times the cosine of the angle between them. So given the angle between them and the magnitudes, we can plug and chug to find the dot product of A and B. Well, how do you calculate the magnitude of a vector given its components? Well, first of all, how do we write a vector in terms of its components? Well, we can write vector A as ax times I hat plus ay times j hat. And we can write vector B as bx times I hat plus by times j hat. So to find the magnitude, which is written using these symbols, of A, we write the square root of ax squared plus ay squared. And to find this magnitude of vector B, we write the square root of bx squared plus by squared. And that is how you compute the magnitude. So now that we've talked about this formula, let's talk about the much more simpler and more intuitive formula. Intuitive in the sense that it's much more easier to compute and easier to remember. So, what is the formula? Well, if you have two vectors A and B and you take the dot product, the result is just ax times bx plus ay times by. So if you know the components, you can just plug and chug it in this formula to get the answer. Well, so let's test it. So over here we have problem 1. We're going to use this formula to find the dot product. Well, let's write A in component form. So A over here is 1, 5. So obviously the component would be I hat over here, and the component over here would be 5 j hat. What about B? Well, B can be written as 7 I hat plus 2 j hat. So, using the formula over here, we have 7 times 1 plus 5 times 2, which is equivalent to 7 plus 10, which is equivalent to 17. So therefore, the dot product of these two vectors is 17. Easy, right? Well, let's make this even more easier. Instead of writing the component form each time, we can make a simple observation and save ourselves from this tedious work. So in other words, if we realize the components are just, so ax is just this, and bx is just this, and ay is just this, and by is just this, we simply can just multiply the top two components and get the value over here, and the bottom two components and get the value of here, and add them together. So in other words, we could have just gone directly into this by saying 1 times 7 is 7, plus 5 times 2 is 10, and adding them together to get 17, and boom, we're done. Okay, now that we've talked about that, we can now talk about the angle. So let's say you want to find the angle between them. How would you progress on doing that? Well, obviously using the second formula, or the one we just used over here, you really don't have an intuition or abstraction about the angles in general. So in order to calculate the angle between two vectors, we can use the formula for the dot product that we talked about earlier. So, A dot B is equivalent to the magnitude of A times the magnitude of B times the cosine of the angle between them. Now notice, since we don't have a calculator right here, we'll just compute what the cosine of theta is. But if you just rearrange the equation once you get the value for cosine of theta and solve from there, you'll find that theta is approximately 62.74 degrees for this first set of problems. Okay, so let's do that. So rearranging this formula first, we'll get A dot B over magnitude of A times magnitude of B is equivalent to cosine of theta. Now we won't proceed forward to solve for theta due to the fact that we don't have a calculator at hand right now, but notice that the angle is approximately 62.74 degrees. So that's what theta is approximately equivalent to. Okay, so let's compute this value. How would we do that? Well, we obviously know that the dot product is 17, so we can write 17 on the numerator. Well, what about the magnitudes? Well, we still have to calculate the magnitudes. So let's compute the magnitude of vector A. This is just the square root of 1 squared plus 5 squared. Well, 5 squared is 25. 25 plus 1 squared, which is just 1, is 26. So therefore, we would get the square root of 26. Now, what about the magnitude of vector B? Well, this is just the square root of 7 squared plus 2 squared, which is 49 plus 4, which is just 53. Therefore, this is just equivalent to the square root of 26 times the square root of 53. So 17 over the square root of 26 times the square root of 53 is equivalent to cosine of theta. Okay, so we won't proceed any further from here because we don't have a calculator, but this is the value that cosine of theta should be equivalent to. Notice that we could simplify this, but that's not of relevance to this video. Okay, now let's move on to the next problem. Now for this problem, we'll go much more faster because we've explained all the nitty-gritty details. Okay, so let's find the dot product of these two vectors. Well, 1 times 3 is 3, and 3 times 1 is 3. 3 plus 3 is 6, so therefore 6 is the dot product of these two vectors. Now what about the angle? Well, A dot B, well that's 6 over the magnitude of A, which is 1 squared plus 3 squared. So the magnitude of vector A, and the magnitude of vector B is 3 squared plus 1 squared, which by commutative property is practically the same thing, but over here we get 9 plus 1, which is the square root of 10, and over here we also get the square root of 10. Now if we do plug it in like this, square root of 10 times square root of 10, we realize that we can simplify this because the square roots cancel, and we just get 6 over 10, which is just 3/5. So cosine of theta should be equivalent to 3/5, and that gives us an angle of approximately 53.13 degrees when we solve for theta. Okay, so now that we've talked about that, we make this section to an end. Faraday and Maxwell made significant contributions to the field of electricity and magnetism. But who were they, what did they do, and how did they do it? Well, let's take a look at Michael Faraday. Michael Faraday started off in poverty and didn't have a proper education, but he loved learning and loved reading books. Eventually, he got a job as a bookbinder, and he read all the books he could possibly read. He realized that he loved experimenting and perfected this skill and became one of the greatest scientists of his time. But what did Michael Faraday do? Well, Michael Faraday is credited with making the first electric generator. Well, what principle was it based on? Imagine a magnet and imagine a coil of wire. You want to produce a specific property or just want to produce something interesting. So what would you do? Well, Michael Faraday decided to move the magnet around the coil of wire, and he realized that this produced an electric field. And this was a very significant discovery. Michael Faraday, along with this, made a lot of significant discoveries which made him one of the greatest scientists of his time. On the other hand, we have James Clerk Maxwell. James Clerk Maxwell made significant discoveries to the field of electromagnetism, and this is due to his mathematical expertise. For instance, consider the Maxwell equations. Maxwell equations are a series of partial differential equations describing electricity and magnetism. The reason Maxwell could write them in their form is due to the fact that he's really good at mathematics. And from countless times in history, we've seen that mathematics is really important in science. From general relativity, such as the Einstein field equations, to the Schrödinger equation in quantum mechanics, mathematics plays a huge role. James Clerk Maxwell once said, "All the mathematical sciences are founded on the relations between physical laws and laws of number," which show how Maxwell cherished mathematics. The cross product is a way of multiplying two vectors together. So let's say you have vector A and vector B. If you take their cross product, the result obtained will be a vector quantity. But if you take their dot product, the result obtained will be a scalar quantity. So let's start by establishing the notation for the cross product. So, let's say you have vector A and vector B. If you want to take their cross product, well, we simply denote by drawing this small x. So this represents A cross B. Now what's the formula for this? Well, it's the magnitude of A times the magnitude of V times sine of theta times unit vector n. The purpose of the unit vector n is to make the resulting vector perpendicular or orthogonal to the plane made by A and B. Now we won't be using this formula to solve this problem in this video, so we won't be talking much about it. So we're going to solve this problem over here using determinants. If you want to learn more about determinants, please visit my videos on determinants. But right now, we're going to go straight to problem solving. But before that, let's talk about the general form of A cross B in terms of determinants. So, we're taking the determinant of I hat, J hat, K hat, AX, AY, AZ, and BX, BY, BZ. If we take the determinant of this 3x3 matrix, we'll get the cross product of the vectors A and vector B. Now, what is AX, what is AY, what is AZ, and what is BX, what is BY, and what is BZ? Well, let's say we have an arbitrary vector A, and we want to write it in component form. Well, we would write it as AXI hat plus AY J hat plus AZ K hat. And if we have an arbitrary vector B, we would write it as B xi hat plus byj hat plus bz k hat. So that's how you would write each of these vectors in component form. And correspondingly, if you put this into the 3x3 matrix over here, and you take the determinant, you would find the answer to A cross B. So let's do that for this problem. So, we're taking the determinant of I hat, J hat, and K hat, then 2, 7, 6, and then 9, 2, 3. So let's write vector A in component form. That'll just be 2i hat plus 7j hat plus 6k hat. What about vector B? Vector B would just be 9i hat plus 2j hat plus 3k hat. Hence we have 2, 9, 7, 2, and 6, 3. So let's take the determinant of this. So if we take the determinant of this 3x3 matrix, we get I hat times the determinant of 7, 3, of 7, 6, 2, 3, minus j hat times the determinant of 2, 6, 9, 3, plus k hat times the determinant of 2, 7, 9, 2. So let me first compute this, and then I'll explain how we got to this. Okay, so if we compute the determinants over here, we get 7 times 3 is 21, 21 minus 12. Well, 21 minus 12 is just 9. So we would get 9i hat plus, if we do it over here, we'd get 2 times 3 is 6, 6 minus 54, so we have to compute that. 54 minus 6 first is 14, 14 minus 6 is 8, 4, 4, and minus plus minus, so minus 48, because 2 times 3 is 6, 6 minus 54, therefore we have minus 48, but minus 48 negates with this, so we get plus 48j hat. Last but not least, 2 times 2 is 4, 7 times 9 is 63, so 4 minus 63, well obviously that'll just be 63 minus 4 first, 13, 4 that's 9, 65, 59, minus plus minus, so negative 59k hat. So this will be the resulting vector of A cross B, but let's just check that. So I hat times 7 times 3, which is 21, minus 6 times 2. Well, obviously that's going to be 9, so 9i hat. Next over here we have 2 times 3 is 6, and 9 times 6 is 54. So 2 times 3 is 6, minus 54, that's minus 48, minus 48, minus j hat is plus 48j hat. And last but not least, we have this. We have 2 times 2 is 4, 4 minus 63, well obviously that's going to be negative 59, so negative 59k hat. So this will be our answer in component form, but if we want to write it in vector form, we would simply do this. We would write 9, 48, and negative 59. This will be our answer. Okay, but let's go back again and explain a lot more details. So to find a 3x3 determinant, what we would do is we would multiply first by I hat, and then we would find the determinant of this small matrix. That's why we have this 7, 6, 2, 3. This symbol represents the determinant. So we're finding the determinant of this small matrix. Now to find a determinant of a 2x2 matrix, A, B, C, D, that's just AD minus BC. That's the determinant of a 2x2 matrix. So therefore, AD in this case is 7 times 3, that's 21. 21 minus 12 times I hat, which just becomes 9 I hat. Therefore, we got the first part correct. Now let's verify the second part. Well, how would we do the second part? Well, we're multiplying the second part by minus j hat, because always we have alternating signs when we do determinants. So, we start with minus j hat, and multiply it by the determinant of excluding 7 and 2, so we have 2, 6, and 9, 3. So, AD minus BC, so 2 times 3 is 6, minus 54, because 9 times 6 is 54, and multiply that by minus j hat. Well, obviously 48 plus 6 is going to equal to 54, so this would be minus 48 because we're doing 6 minus 54. Minus 48 times minus j hat is just positive 48 j hat, so we would get positive 48 j hat, which is indeed what we have there, and therefore that's correct. And last but not least, for k hat, we're taking the determinant of this 2x2 matrix. We're taking that determinant. So we have k hat times 2, 7, 9, 2. Well, obviously, 2 times 2 is 4. 7 times 9 is 63, minus 63. And multiplying that by k hat. Well then, 4 minus 63, well, obviously 59 plus 4 is 63, so 4 minus 63 is minus 59, and therefore we get minus 59 k hat, and we have minus 59 over there. And that is how you find A cross P using determinants. Now, if you want to learn more about how to find determinants for 2x2 matrices and 3x3 matrices, please visit my other videos on determinants where I explain more thoroughly how to find the determinant of matrices. Okay, now that we've talked about that, we need to make this section to an end.